Let's take a closer look at how LWPython prepares to jump to a function. Python first evaluates the function call arguments, then constructs the function input map. The keys in this map are the function parameters, and the values are the corresponding function call arguments. For example, consider the following function header. The parameters are x, y, and z. Suppose that we call this function as follows. The arguments are 5, 6, and 10. LWPython creates the function input map with 3 entries, x5, y6, and z10. The number of function parameters must match the number of arguments in the function call. Also, the parameters are matched with the arguments in the order they appear. Thus, the first parameter x is matched with the first argument. The second parameter y is matched with the second argument 6, and so on. Next, Python saves the current Python state in the context stack. More precisely, Python bundles the local variables map, the expression stack, value stack, control map, line, and tab, and pushes this bundle to the context stack. Python is now free to overwrite the Python state. Python first copies the function input map into the local variables map. Then it resets the expression stack. Finally, Python updates line to the beginning of the function body and tab to 1. Try running the simulator at logicwalk.org to see how Python prepares to jump to a function. Why is Python using a stack to store the Python state? Would the context stack ever contain more than one element? Suppose that a program calls some function A. Python will push the current state to the context stack. Now suppose that function A's body contains a call to function B. As Python prepares to enter function B, Python will again push the current state to the context stack. Context stack now contains 2 elements because LWPython has not popped from the stack yet. Python then executes function B's body. At the end of function B, LWPython pops the context stack and restores the state of the call site in function A. Finally, when Python exits function A, the context stack is popped again to restore the state of the original call site. As we can see, every time we make a function call, the context stack grows by 1. Then, as Python completes the function calls, the context stack shrinks, eventually becoming empty again. The stack data structure is perfect for saving and loading Python state, because the load operations occur in reverse order of the save operations. In other words, the last saved state is the first loaded state.